All right, let's talk about forces. So far we've looked at objects moving in terms of kinematics, right? So we've looked at how fast something is going, how much time does it take, what's the distance it travels, what's the rate of change in its velocity, right? What's its acceleration? But really, kinematics is the very basic, bare bones description of motion, right? You can say that something is accelerating, but you don't necessarily know why it's accelerating. So forces is going to fill in the blanks here and give us a reason as to why these accelerations occur. Now, if we want to define a force, right, a force can simply be defined as a push or a pull. Now, keep in mind that forces only exist as a result of interaction between two or more objects, right? If you were able to take one object somehow and magically isolate it from every other object in the universe, that object would never experience a force, right? Because there needs to be interaction between an object and an agent in order for forces to occur. Now, one thing to keep in mind, we'll cover this again when we talk about Newton's first law, is that, again, forces are not necessary for motion, right? Something can be moving along with no forces acting on it. Right? The only evidence that you have of some external net force is if the object is accelerating, right? If it's speeding up, slowing down, or if it's changing directions. Now, forces are going to be measured in newtons. 1 newton is defined as 1 kilogram meter per second squared. Your forces are also vector quantities, meaning the direction matters, and will be showing forces acting on objects in things that we call free body diagrams. And that's something that we'll cover here towards the end of this video. So let's just start by talking about a few forces. So if you look at the notes, we have there listed 4 fundamental forces of nature. By that, we mean that these 4 forces are critical to shaping reality as we know it. So the first fundamental force we talk about is gravitational force. Now, the reason we say that the gravitational force is a fundamental force is because the gravitational force allows for the overall macroscopic structure of the universe, right? It allows for planets to form. It allows for those planets to orbit suns. It allows for those solar systems to orbit a black hole in the center of the galaxy, right? So the gravitational force gives us the overall big structure of the universe. Now, the electromagnetic force is the force responsible for compounds being able to form, right? That electromagnetic attraction between things allows complex matter to exist. Now, we'll only cover the electric side of the electromagnetic force. If you want to do magnetism, that's AP2. But keep in mind, yes, we cover electric force and magnetic force separately a lot in physics, but really, they're the same force. They're the electromagnetic force, right? We used to think that they were 2 distinct forces up until, I believe it was in the 1800s, where you had a Danish professor, Ørsted, who was giving a lecture on circuits. Right? So he had a circuit on his desk, and he just happened to have a compass sitting on the table as well. Well, when he activated the circuit, what he noticed was the compass needle would respond to the flow of electricity. And so he started to piece it together that, hey, these 2 forces are not separate, right? It's one force, the electromagnetic force, just 2 different sides of the same coin. Now, your strong nuclear force is what's responsible for allowing the nucleus to exist, right? Think about what you have in the nucleus. You got a bunch of protons and neutrons. Well, protons are all positively charged. They shouldn't be able to be that close to each other, right? They want to repel each other electromagnetically. Well, there's a stronger force in the electromagnetic force, that strong nuclear force that's keeping them bound within the nucleus itself. And then the weak nuclear force dictates how energy is released from the nucleus itself, right? It dictates your radiation, alpha, gamma, beta, so on. Now we can break our types of forces into 2. So forces can either be contact forces, or they can be field forces, or action at a distance forces, as they're sometimes called. Now, your contact forces mean exactly what it sounds like they mean. It means that the 2 objects interacting have direct physical contact. Whereas your field forces, right, those are forces that can act over a distance. So most common contact forces that we will be dealing with this year are your frictional force. Now, whenever we're dealing with forces, capital F is always going to stand for force, and then the subscript is going to tell you what type of force you're dealing with. So F sub F is friction force. Tension force is F sub T. Now your tension force, that is your force associated with ropes and strings, right? So pulling a cart by a rope, right, that'd be tension. Your normal force is F sub N. Now your normal force, that's the force of a surface pushing back up on an object, right? So look at something on your desk. Say you have a bottle of water there. Well, why doesn't the water fall through the desk? Well, the table is exerting an upward force on that bottle of water, right? And that force we call the normal force. Right, if I lean against the board, well, I'm not falling through the board. The board must be pushing back on me, right? So it's exerting a normal force on me. Now, the reason we call it a normal force is because normal is just the term mathematically for perpendicular. So the normal force is always perpendicular to the surface the object is resting on, right? So for instance, if you've got yourself your table and you've got yourself your bottle of water here, well, the force exerted on the water bottle by the table is directly upwards, right? And if we extend this, notice that that force is perpendicular, it's normal to the surface of the table itself. So that's what normal force means. It's giving you an actual mathematical relationship between the surface and the force exerted. Air resistance we'll barely ever see. Applied force would just be F sub A. And your applied force is just the generic force of pushing or pulling, right? So if I pull on a table, I'm applying a force. And lastly, we'll look at a lot of spring forces as well. And spring force is going to be F sub K, right? So K is the designator for springs. And once you see the spring force equation, that'll make sense why. All right, as far as your action at a distance forces go, those are forces that do not require direct physical contact. So they can act over a distance. There's a field around these objects wherein a force is exerted. So your three big ones are your gravitational force, which would just be F sub G, your electric force, F sub E, and your magnetic force, F sub M. Right, so take for instance a ball. You throw a ball straight up in the air. Well, why does it come back down? There's a gravitational force acting on it, right? Is the ball in direct physical contact with the earth? No. Right, so the earth is exerting that gravitational force on the ball over a distance. All right, let's talk about Newton's first law. So Newton's first law is often called the law of inertia. And you guys have probably, recited it since middle school, right? Objects in motion tend to stay in motion. Objects at rest tend to stay at rest unless acted upon by an outside force, right? And that's all fine and well, but we can boil it down to a much, much simpler and concise definition for the first law. So the first thing we want to do is just define what inertia is. Right? Inertia comes from the Latin for lazy. Basically what we're saying when we're saying that objects have inertia is that objects don't like to change what they're doing. They're lazy. They want to keep on keeping on. If it's at rest, it wants to stay there. If it's moving, it wants to keep moving in a straight line at a constant velocity, right? At a constant speed. So objects resist these changes in their states of motion. And the more inertia something has, the more mass something has, the more inertia it has. Right? It's easier to stop a toy car than it is a moving bicycle, right? So mass is directly tied to the idea of inertia. More mass, more inertia. Now, we define inertia as resistance to changes in states of motion. What are we talking about when we're talking about state of motion? What we're really talking about are changes in velocities. So we can boil inertia down to a simple definition of resistance to acceleration. So the more mass something has, the more resistant it is to being accelerated. So if we want to restate Newton's first law in those terms, Newton's first law simply states that objects resist acceleration. Objects do not want to accelerate unless they're forced to by an outside force. Alright, so there's a resistance to acceleration. Now, here's the problem. There's a big misconception here, especially when we're talking about Newton's first law. People always want to say that if an object is moving, it means that a force has to be acted on. And the reason people believe that is because we live in a world that is full of friction, right? So take, for instance, this chair here. Right, I give this chair a push. Well, what does it eventually do? It eventually stops, right? And so people go, aha, right? That is evidence that that chair will naturally come to rest unless I continue to push on it, right? It's evidence that I need to continue to exert a force on this for this to continue moving, right? And so that's an idea that dates back to the ancient Greeks and Aristotle, right? The idea that objects want to stop naturally. Well, here's the problem. That chair stopped not because it's naturally wanting to stop, it's because there is an outside force acting on the chair. The outside force in this case was the force of friction, right? Friction is what caused the chair to stop. If we had a frictionless track and I did that with the chair would continue to move at a constant speed in a straight line, right? So objects resist accelerations unless there's an outside force acting on them. And again, in that case, that force was friction. Now, we can have two scenarios of forces acting on objects. Right? The object can either be in equilibrium, meaning that all of the forces are balanced, right? Your leftward forces equal your rightward forces, upward equal your downward. Or it can be in a state of imbalance, meaning that you have a net force. Now, when we're dealing with equilibrium, it makes your life a lot easier. Because in equilibrium, we know that it can only be in two states. Right? Equilibrium means that your forces are balanced, so you have no net force, meaning that your acceleration is zero. Which means that the object can only be doing one of two things. It can either be at rest, or it can be moving with a constant velocity. And keep in mind, again, it's these imbalance in the forces that cause an object to change its velocity, to accelerate. So in the notes, there's a conceptual example. And it tells us that Ben is being chased through the woods by a bull moose that he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating, yet if Ben makes a zigzagging pattern through the woods, he will be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. So go ahead, pause that, see if you can't come up with an explanation that uses proper terminology. Alright, if I wanted to explain this, well, the bull moose has a much larger mass than Ben does, which means that it has a much greater resistance to acceleration, to a change in velocity. Well, think about what's happening when you zigzag. When you zigzag, you're changing directions, which by definition is an acceleration. So Ben, with his lower resistance to accelerations, is able to change directions much more easily. Now, that's something that you see all the time. Like on the football field, a smaller guy can make cuts better than a bigger guy. You see it in nature. For instance, I've got a dog I've got a red heeler, and so it's about knee-high, right, about 60 pounds. My buddy, he's got himself a Great Dane Labrador mix, right, which is basically a small pony. Well, one day, they're out in the backyard together, and his dog starts chasing my dog. Well, my dog heads straight for the fence, and at the very last minute makes a quick cut. Well, she's able to do that because she's got a much lower mass. and a smaller center of gravity, but we'll get to that later. His dog, meanwhile, can't quite make that turn, ends up running into the fence, right? So it's that idea of inertia and the resistance to acceleration, which includes changes in direction. Now let's look at free body diagrams. There are a couple rules for your free body diagram that you got to follow. Now, you always start with your object. It can be a square, it can be a circle, doesn't matter. You don't actually have to draw the object out. Now, let's say we're doing a free body diagram for a bottle of water sitting on a table. Now, we've got two forces acting on that bottle of water. You've got the gravitational force downwards, and you've got the normal force of the table pushing back on the water. Now, your vector arrows always have to start from the object itself. So, force of gravity would be pulling downwards. Now, again, make sure that your vectors originate from the object. You can never have force vectors pointing at the object in a free body diagram. So, if you did something like this, well, yes, you've indicated correctly the direction of the force of gravity, but it's just not proper convention. You can't have the vector pointing at the object itself. So, we've got force of gravity. And we've got force normal. Now, I made these roughly the same size. Why? Because they're the same size force. So the length of your force vector arrow tells you the magnitude. So if you're drawing a free body diagram and you have a force that is much greater than another force, make sure that that line is longer than that other one. I mean, if they're identical forces, they don't have to be exactly the same, but they should pass the eyeball test. Now, I'm going to be posting up some practice with free body diagrams. I'll post the key up there as well. Number 5, I believe it is, I don't have it in front of me, deals with a football or with a quarterback being tackled. That free body is going to be up to a lot of interpretation depending how you're picturing this quarterback being tackled. So just keep that in mind. But yeah, I'll be posting that up, so take care of that, and then I will be posting up some concept builders to reinforce the free body diagram stuff. All right, see y'all.